What injection system? A high pressure. A low 15% differentiate between the high and the low pressure fuel systems. Diesel engine fuel systems have two main divisions, differentiated according to their operating pressure. One system, examined in detail in a previous chapter, is the low-pressure fuel supply system. Low-pressure supply systems store, condition, and transfer clean, vapor-free fuel at the correct temperature, pressure, and volume to the high-pressure injection system. Operating pressures of the low-pressure system rarely exceed 100 pounds per square inch and commonly operate below 75 psi. The second fuel system division is the high-pressure injection system, which pressurizes fuel to tens of thousands of psi or bar, enabling it to rapidly inject fuel into each cylinder's combustion chamber. High-pressure injection systems are unique to diesels, functioning to deliver a precise amount of fuel to each cylinder at the correct time, which allows it to be efficiently combusted. In fact, high-pressure injection systems are a diesel's most distinctive feature and perform one of the most fundamental operations of a compression ignition engine, injecting diesel fuel into each cylinder. Pressurizing fuel to very high levels is necessary to inject large quantities of fuel into combustion chambers during a small window of time in the operating cycle that can span less than 3 milliseconds. Extreme pressure is also necessary to spray liquid fuel through very small injector spray orifices, barely visible to the human eye, causing it to convert to small droplets that penetrate and mix with hot, dense air. Once liquid fuel is broken down into small particles inside the cylinder through a process called atomization, fuel droplets form a fog-like air-fuel mixture that can easily burn after they absorb heat. To convert low fuel pressure to pressures required for injection, high-pressure injection systems commonly depend on nozzle, fuel in valve fuel pump piston cam. Figure 15%-1, the high-pressure fuel system injects, distributes, and atomizes the fuel while overcoming the resistance of air made dense by cylinder pressure. Camshaft-actuated plungers operating inside barrels. Cam and plunger assemblies supply the mechanical force acting directly on fuel supplied by the low-pressure system. Camshaft-driven plungers and barrels used to multiply fuel pressure are incorporated into either an engine-driven hydraulic pump or as a device pressurizing fuel inside injection pumps, unit injectors, and unit pumps. A nozzle valve that sprays fuel through small orifices is the other essential element of the high-pressure injection system. How well the injection system can do its job to control the delivery of fuel has an enormous influence on engine power output, fuel consumption, noise, vibration, and emissions. Efficient diesel engine operation relies on each injection event delivering a precisely controlled quantity of fuel, injected. Figure 15-2 high pressure is needed to convert liquid diesel fuel into a fog-like air-fuel mixture by using an injector nozzle. Plungers and barrels drive gear fuel injectors camshaft. Figure 15%-3 camshaft actuating pumping plungers are one of the most common mechanisms used to pressurize fuel to high injection pressures. At high pressure, and at the correct time into the combustion chamber. These basic functions are so critical that the injection system might be considered the most central system or the heart of diesel engine operation. The importance, complexity, and technical refinements of the high-pressure injection system are reflected in its high cost relative to other engine systems. As the costliest engine system, the injection system is not only designed, constructed, and operated with the greatest precision, but also requires equally sophisticated service skills and techniques supported by superior technical knowledge of its operation. Although there are a number of essential elements common to every injection system, there is no single type or design of high-pressure injection system used by all diesels. The same way that spark ignition engines will use either a carburetor, direct or port-type injection system to deliver fuel. Instead, an enormous variety of high-pressure injection systems exist and are radically different in terms of their construction, complexity, and operating principles. Consequently, studying to identify and learn the differences between the various types of high-pressure injection systems can be overwhelming. To overcome this problem, this chapter will examine high-pressure injection system operation by first identifying and explaining system functions common to all injection systems. This foundational information about common injection system functions becomes the lens through which to view more detailed descriptions of specific systems in subsequent chapters. Analyzing high-pressure injection systems in terms of what category they belong to and how each of them perform common functions is not only helpful to understand injection system operations, but also necessary to develop the skills related to diagnosing, servicing, and maintaining diesel fuel injection systems. Purpose of high-pressure injection systems. The high-pressure system is a diesel engine's most distinctive feature and one of the most fundamental elements of compression ignition engines. High pressurization of miscellaneous 14% turbocharger, fuel system 12% crankshaft assemblies, 8% valve train, 7% cylinder, block 6% cylinder, head 5% exhaust gas recirculation, 2% cooling system, 1% engine covers. Figure 15% compared to other engine systems. The high-pressure fuel system is the most expensive in manufacturing a diesel engine. VP44 distributor injection system, CRS common rail system, unit injector system, up unit pump system, fuel rail injector distributor high pressure pump. Figure 5.4. The most common diesel injection systems currently using either high pressure pumps or camshaft actuated plungers and barrels. These systems are distributor pumps, common rail, unit injection, and unit pump. Fuel for delivery by the injection system is necessary for several reasons. 1. Fuel must have sufficient pressure and energy to penetrate the dense combustion chamber MS. Air compressed at high pressures in the chamber makes it even more difficult to distribute fuel through tightly packed air molecules. 2. High-pressure injection enables the injection event to take place in less time than it takes a camera to flash. Rapid injection is needed at high rotational speeds because only a short of time is available to deliver all the required fuel mass. After injection, additional time is needed for fuel to atomize, distribute, and mix with air, and then to absorb heat, convert to vapor, and begin burning near the end of the compression stroke. These combustion events take place just before or slightly after the piston reaches top dead centered, only near the end of the compression stroke. Injection events must be performed quickly to allow the bulk of the injection volume to enter the chamber and provide adequate time for the subsequent combustion event. Rapid completion of injection events is possible only when fuel is highly pressurized, and this is especially important as engine speed increases. Time available for injection events shortens as the engine speed increases, so increasing injection pressures proportionate to engine speed is necessary to quickly deliver fuel to the combustion chamber. 3. High pressure is necessary to break up the liquid fuel into a fine mist. This process, called atomization, is enhanced with high injection pressures. Progressively higher pressurization produces increasingly smaller droplets of fuel that readily absorb heat and burn. Improving atomization, which is to make fuel droplets smaller, and Figure 15-6, high-pressure injection systems spray fuel into the combustion chamber through a fuel nozzle. Multi-orifice nozzle fuel in nozzle body exposed annular area pressure chamber, needle valve nozzle SAC or blind hole, pintle nozzle fuel in nozzle body nozzle needle, annular area pressure chamber, pintle spray orifice. Figure 15-7. All high-pressure injection systems use a fuel nozzle to atomize highly pressurized fuel. Figure 15-8. Better atomization of fuel into smaller, finer droplets produces a cleaner and faster burn period. More numerous results in more efficient combustion as well as better fuel economy, increased power, and lower emissions. See the fuel atomization section of this chapter. In today's engines, injection pressures range from a low of around 3,200 psi during idle conditions to over 42,000 psi or more, from amplified common rail injectors operating at high speed under full engine loads. Light-duty diesels may use even lower pressures at idle speed to reduce combustion noise. Higher peak injection pressures are being planned for future manufacture, with developmental engines now achieving as much as 60,000 psi. An enormous variety of high-pressure fuel systems are available to deliver fuel to each cylinder in a diesel engine. However, all these systems perform common tasks that, when recognized, can simplify the understanding of how a particular fuel system operates, as well as develop strategies to maintain, diagnose, and repair them. Safety tip. The dangerous consequences of working around high-pressure fuel that cannot be overemphasized are the injection of pressurized fuel into hand or finger tissue. Fluids require a pressure of only 100 psi to penetrate the skin, and much less pressure to penetrate an eye. After penetrating the skin, fuel creates an intense inflammatory response because it spreads quickly and chemically destroys tissue. Vast areas of tissue may be destroyed through a secondary infection that may occur if the injury is left untreated. After the skin is initially penetrated by pressurized fuel, there is minimal pain, dependent upon the amount of fluid injected. Because it is not painful at first, technicians might delay treatment, which allows the fuel to spread and damage a larger area, increasing the likelihood of complications and even amputation. Therefore, it is never safe to check for leaks from injection systems with a hand. Instead, use a piece of cardboard or paper and wear additional appropriate personal protective equipment. Figure 15-9 disposable nitrile gloves are recommended personal protection for working with fuels, solvents, grease, and oil. Nitrile is frequently identified as a blue or black-colored glove, recommended by the original equipment manufacturer, which goes beyond the mandatory safety glasses and nitrile gloves required when working with fuel. Technician tip: disposable gloves for hand protection are essential when working with fuels, oils, and grease. Although diesel fuel is not currently considered toxic to humans and is not considered to be a reproductive or developmental hazard, diesel fuel can be absorbed through the skin and cause irritation. There is some limited evidence derived from animal studies that indicates prolonged exposure to diesel fuel may increase the risk of developing skin cancer. This means there is little risk of developing cancer from short-term or occasional exposure, but daily exposure to diesel fuel over long periods of time may result in kidney damage and cancer. For the personal protection of a technician, nitrile gloves are recommended to resist chemicals in grease, oils, and solvents such as gasoline, diesel fuel, and aerosol. Nitrile is a synthetic material made to improve on the protective properties of latex gloves. They can be made thinner, stronger, and more puncture-resistant while transmitting a better contact, feel, through the material without giving up any protective properties. Fluoroelastomer gloves are tougher and will not swell in any solvents but are very expensive. Neoprene gloves are not recommended because they will swell and quickly deteriorate in most hydrocarbons. Functions of high-pressure fuel systems. Low 15.2 identify and list the functions of a high-pressure fuel injection system. All high-pressure injection systems perform the following tasks: meter the correct quantity of fuel for each injection event. Time the injection event to begin delivery of fuel at an optimal point in the operating cycle. Control the rate of fuel delivery. Atomize the fuel and distribute the fuel throughout the combustion chamber. When any of these functions are deficient, engine performance and emissions-related problems are present, and further mechanical problems will likely develop. Engine noise, vibration, excessive fuel consumption, and visible emissions will usually accompany complaints about poor performance. While performing these functions, the system must use design and construction features to reduce or eliminate unwanted interference caused by the hydraulic behavior of pressurized fuel. For example, transmission of high-pressure fuel through lines and the abrupt beginning and ending of fuel flow for an injection event is accompanied by powerful pressure waves that can disrupt the injection event. Injection systems must build in features to minimize the negative impact of conditions caused by movement of highly pressurized fluids. In these next sections, several of these negative behaviors are identified, and each of the functions common to all high-pressure injection systems is described in more detail. Fuel metering. Metering is the process of measuring the correct quantity of fuel delivered to each cylinder during each injection event. It is important to remember that diesel engines only meter fuel to regulate power output and do not use a throttle plate in the air intake to adjust engine speed and torque. Unthrottled air intake into a diesel allows maximum airflow into the cylinders, enabling it to produce high torque output at low engine speeds by simply injecting the correct quantity of fuel. Increasing or decreasing combustion pressure inside the cylinders changes engine torque output or speed. Metering measuring. Diesel fuel. Speed plus torque. Figure 15-10 metering is the process of measuring the correct quantity of fuel required for each combustion event. Engine speed and torque output are controlled by metering fuel, depending on the engine load. If the operator demands more power, more fuel is injected to increase cylinder pressure in order to maintain engine and vehicle speed. Increasing the injection quantity without a proportional increase in engine load will simply increase engine speed. Likewise, reducing the quantity of fuel metered for delivery lowers engine speed and/or torque. Because the amount of fuel required for each injection varies with engine speed and load conditions, the fuel system needs a mechanism to correctly sense, measure, and adjust the precise quantity of fuel for delivery. The engine governor performs the sensing function for the metering system. Measuring and adjusting the quantity of fuel for injection will depend on either mechanical mechanisms or the use of electronic control systems that generate electrical signals to operate electromechanical devices, such as injectors. Technician tip: High compression ratios, turbocharging, and longer crankshaft throws are just a few of the major reasons why diesels produce higher cylinder pressures and greater torque output. Another major reason for higher torque at low engine speed is the absence of a throttle plate that limits intake airflow. Without restriction to airflow, maximum air volume can enter the cylinders and provide more oxygen to properly combust larger quantities of fuel. Fuel metering and the role of governors. All diesel engines use a governor to regulate the engine speed and torque by varying the quantity of fuel delivered to the cylinders. The job of an electronic governor in a high-pressure injection system is to correctly sense or calculate the quantity of fuel an engine needs to operate. Governors are part of the metering system but do not actually meter fuel. Instead, they regulate engine speed and torque by signaling fuel metering mechanisms, either mechanically or electrically, to measure out the correct amount of fuel for delivery. Essentially, the governor will sense the engine speed and load and combine this information with driver demand to determine how much fuel the high-pressure injection system should deliver to the cylinders. A separate fuel metering mechanism is used to convert the demand for fueling from the governor into an actual volume or weight of fuel for injection. Whether it is mechanical or electronic, the governor receives inputs from a minimum of the vehicle's throttle pedal, engine speed, and intake manifold or boost pressure to calculate how much fuel should be injected, and whether to increase, decrease, or continue using the current injection quantity. Based on input to the governor, a mechanical governor uses mechanical linkage to move fuel metering controls to vary injection volume. If it is an electronic governor, a set of programmed control logic steps. Low combustion pressure, less torque; high combustion pressure, more torque; main bearing journal, crankpin, throw length equal to length. Torque combustion pressure x length of throw. 15-11 Injecting more fuel produces higher combustion pressure. Higher combustion pressure produces increased torque. Governor high pressure pump. 15-12 Whether it is an electronic or a hydromechanical injection system, the governor functions in the high pressure injection system to regulate engine speed and torque output. Results in a command for a specific quantity of fuel to be injected. Programmed logic used by the governor is part of other software routines stored and executed by the engine control unit, or a separate fuel injection control module. Fuel injection control software operating microcontrollers then generates the appropriate electrical signals to energize injector circuits tasked with delivering the correct amount of fuel requested by the governor. The governor request for fuel and the quantity of fuel delivered by the injectors connected to metering circuits is reported as commanded volume or mass compared to actual delivery quantities. To help understand, the equivalent of a diesel governor in a gasoline or Otto cycle engine is the throttle plate. In those engines, the operator opens and closes the throttle plate with a foot-operated accelerator pedal. The operator or the cruise control system, when engaged, makes decisions about how much engine speed or torque is desired and moves the throttle plate to a position that achieves the desired result. The diesel engine throttle, however, does not operate the same way. For a diesel, the operator's accelerator pedal or throttle lever is only one of several inputs to the engine governor, and the operator doesn't directly control the amount of fuel injected. Several other inputs, in addition to driver or operator demand, are required to adjust engine speed and torque output. Metering units of measurement. Because injection systems commonly use camshafts and plungers to pressurize fuel inside barrels, units of measurement for injection quantities delivered to combustion chambers are traditionally volume measurements and reported as cubic millimeters. This delivery volume corresponds to the displacement of a plunger pressurizing fuel, and this liquid volume can be measured in a graduated cylinder. More recently, manufacturers have been using fuel weight or mass as measuring units to report metering quantity. Mass measurements are even more accurate because they account for differences in fuel temperature, which changes fuel density. Mass measurements are also more compatible with ECU calculations for measurements of exhaust gas recirculation and intake airflow, which are also measured according to mass or weight. Electronic governor controls. The advantage of an electronically controlled governor over a mechanical one is that the electronic governor is better able to control engine fueling according to operating conditions and to do so with greater precision. With inputs to the governor enriched by more sensor and controller area network data than a mechanical governor, fueling is better matched to operating conditions. For example, consider an electronic governor that typically receives data from the fuel temperature sensor. Fuel temperature data are used to apply a correction factor to the quantity of fuel injected to compensate for changes to fuel density that occurs with temperature changes. This is important because as the fuel temperature increases, its density decreases. A loss of power can occur if the same volume of hot, less dense, energy-deficient fuel is metered compared to the same volume of cooler, denser fuel. Other sensor inputs that influence engine fueling tasks performed by the governor include those associated with protecting the engine through derating or shutdown. Sensors input data from oil temperature, oil pressure, coolant level, and the air temperature, and then supply information to the engine protection system. Through the governor, the engine. All instruments, chart case control, EGR engine, brake, fuel system, mechanical switch. Second 15.
This screenshot shows a mass measurement of the weight of fuel metering will derate or even shut down an engine if it detects abnormal operating conditions that may potentially result in catastrophic engine damage. For example, excessive intake temperatures caused by an externally blocked charge air cooler could result in damage to cylinder components due to excessive combustion temperatures. Metering control systems. LO 15.3 identify and describe common injection and metering control systems. Metering control mechanisms measure out the precise quantity of fuel for injection into each cylinder of the engine. How they adjust the injection event's delivery volume or change the mass of fuel for the injection event is the area of technology where diesel injection systems widely diverge in terms of construction and operating principles. Categories for metering systems can be broadly grouped into either mechanical or electronically controlled metering mechanisms. Solenoids and control valves, energized by electronic control units, will essentially operate as gates that open or close hydraulic circuits to allow pressurized fuel to enter a spray nozzle or control the beginning and end of a pressurization phase of an injection event. Mechanical mechanisms operate to limit or extend the effective travel distance of camshaft-actuated plungers that pressurize fuel for injection. Changing the amount of time and pressure of fuel supplied to a high-pressure pumping plunger is another technique for metering the injection quantity. Mechanical metering mechanisms were frequently incorporated into early unit injection, inline, and distributor-type injection pumps. To get a sense of how injection systems are vastly different in terms of construction and operation, consider that all three types of injection systems used a camshaft lobe to actuate a high-pressure pumping element dedicated to each cylinder of the engine. Despite the operational similarities, systems is physically very different from one another. For example, multiple plungers are enclosed. Nozzle control valve. Figure 15% common rail injectors that use electrohydraulic solenoids to open and close the troll metering. Graduated cylindered injector. 18% during repair. This comparator bench is used to measure the quantity of fuel metered and delivered by multiple types of injection systems. Testing and adjustments of metering mechanisms are made on a comparator bench, in a single housing of distributor and inline injection pumps for multi-cylinder engines. Unit injectors house plungers separately for each cylinder and do not have an internal camshaft. Inline injection pumps and early mechanical unit injectors will use either a port helix or sleeve-type metering system to vary the quantity of fuel pressurized for injection by each pumping element. Distributor pumps use neither of these metering systems. Common categories of metering systems include port helix metering, used by inline injection pumps and some Detroit diesel and Caterpillar mechanical-type unit injectors. Sleeve metering, Caterpillar mechanical-type inline injection pumps. Opposed plunger metering, distributor-type pumps such as Rusamaster and Stanadyne. Axial plunger metering, Bosch distributor-type pumps. Pressure-type metering, older heavy-duty Cummins engines and Cummins ISX engines. Electronic unit injection and unit pumps. Newer Detroit, Mack, Cummins, Volvo, and other HD engines. Common rail, used by all current medium-duty and HD diesels. Each of the above metering systems has variations and subtypes depending on such factors as production dates, manufacturer, and level of refinement. The operating principles and construction of each of these metering systems is covered in detail in subsequent chapters of this text. But to provide an understanding of just how wide the categories of metering mechanisms and types of injection systems frequently used by diesel engines are, the following sections offer a brief overview of common injection system configurations. Port helix metering systems. Developed by Robert Bosch, the earliest compact high-pressure injection systems and governors took large, heavy diesel engines. System. Out of industrial factories and off ships and put them on roads and farms. In the late 1920s, Bosch designed and produced compact multiple plunger injection pumps using what is called a port helix metering system, and that were controlled with his patented mechanical governors.
These injection pump design elements are combined to produce a multiple plunger injection pump. A multiple plunger injection pump is a fuel system configuration that uses piston-like barrel and plunger assemblies that are actuated by a camshaft lobe to pressurize fuel for injection. To vary the quantity of fuel required for injection, a port helix metering system has a helix-shaped groove machined into the side of the plunger that rotates inside the pump barrel. The barrels are supplied low pressure through an inlet or spill port. Upward movement of the plunger pressurizes fuel for injection. The injection quantity is varied or metered by rotating the plunger's helical groove orientation with the spill port. A control rack rotates all the pump's plungers back and forth to change the point during the plunger's stroke, when the helical groove uncovers the spill port and ends pressurization of fuel above the plunger. The control rack and governor are responsible for rotating the plunger in the barrel to change the effective length that the plunger stroke travels to displace and pressurize fuel for injection. Pumping elements, each consisting of a barrel and a plunger, are arranged in line in a pump housing for each engine cylinder. The pumping elements share a common governor, camshaft, and fuel charging system that supplies low-pressure fuel to each pumping element. Some pumps that use port helix metering systems are constructed from V-shaped housings with multiple plungers arranged in line in each bank of fill, port control, flange, spill, port barrel, plunger control, rack, pinion gear. Figure 15%-20 to meter injection quantity. A control rack rotates the orientation of the helical groove to the spill port in order to vary the amount of fuel for injection. The pump. Regardless of the pump housing shape, each pumping or pressurization element is connected to an injector nozzle through a rigid, high-pressure fuel line. Because this arrangement of high-pressure components uses a line and nozzle, these injection systems are referred to as pump line nozzle fuel systems. Bosch licensed many of its designs to companies such as Lucas Cav, Nippon Denso, American Bosch, Zegzel, Diesel, Kiki, and others. Drive shaft delivery valve holder, WW delivery valve, plunger barrel control rack, camshaft governor, speed control lever. Figure 15-21 major components in a multiple plunger injection pump. A pump-mounted camshaft actuates plungers that pressurize fuel for injection. The control rack links the pump to the governor. Contemporary multiple plunger injection pump systems consist of the following: a high-pressure injection pump that has more than two pumping elements, a mechanical or electronic governing system, air-fuel ratio controls, an optional timing device to vary the start of injection, high-pressure fuel lines that connect the pumping elements to a fuel injector in each cylinder. Sleeve metering systems. Sleeve metering systems were introduced by Caterpillar in the early 1970s. Like the port helix system, sleeve metering uses a plunger and barrel assembly to pressurize fuel for injection. Instead of rotating a plunger to vary the metered quantity of fuel, a movable, close-fitting sleeve opens and closes a spill port drilled into the plunger. Another drilled passageway connects the top of the plunger with the spill port through a cross, drilling in the plunger. Upward, reciprocating movement of the plunger pressurizes fuel for injection as long as the sleeve covers the spill port. When the sleeve position, which is variable, uncovers the spill port, pressurization ends. The name given to the sleeve metering system is based on the use of a sliding sleeve that is positioned by governor linkage. To increase the injection quantity, the governor control shaft and fork raises the sleeve higher over the plunger. This position enables the spill port to remain closed for a longer effective plunger stroke travel, pressurizing fuel while the camshaft applies force to the bottom of the plunger. Lowering the sleeve position, in relationship to the spill port on the plunger, shortens the plunger's effective stroke and reduces the quantity of fuel allowed to be pressurized inside the barrel. Barrel, plunger fill, port spill, port metering sleeve, figure 15-22 components of the sleeve metering system. Opposed plunger metering. To reduce the number of parts and injection pump complexity, distributor-type injection pumps use a single pumping element and metering system instead of multiple plungers to pressurize and meter fuel for all the engine cylinders. Mechanical distributor pumps, manufactured at a much lower cost than multiple plunger injection systems, began widespread use. Injection nozzles orifice, bleed-off injection pump fuel return, key fuel tank fuel filter, water separator, and heater, fuel supply, pump fuel supply line. Figure 15-24, a common configuration for a distributor-type injection system. in the early 1950s and were critical to the placement of diesel engines in farm machinery and passenger vehicles in the 1970s. The type of fuel metering system they use classifies various types of distributor injection pump designs and operation. Two metering systems commonly used are 1. Opposed plunger metering. Sometimes called radial piston, this design uses inlet metering principles. Standardine Corporation, later owned by Delphi, uses this pump, and its licensees are based on the Elia-Rusa master pump design. 2. Axial piston metering. This design has a sleeve metering system similar to Caterpillar's sleeve metering system, which uses a close-fitting sliding collar to open and close a spill port on a pumping plunger. Mechanical injection pumps that use axial piston metering systems were developed by Bosch and used by its popular Bosch V-pump and Bosch licensees. Opposed plunger metering systems were used in the first popular distributor pump design. They pressurize fuel between 2, 3, or 4 small opposed pistons. Because the pistons are arranged opposite one another, it is called an opposed plunger or sometimes a radial plunger metering system. Pumping plungers, which pressurize fuel, operate inside a stationary cam ring that could be described as a donut hole with lumps. This cam ring is the equivalent of the camshaft in a multiple plunger pump and is used to provide the actuation force needed to pressurize fuel. Rotating the engine-driven rotor, also called a distributor shaft, forces the pumping plungers together and holds them inside the stationary cam ring when they contact a raised lobe on the cam ring. Pushing the plungers together will pressurize fuel between opposed plungers as they follow the profile of the cam ring. Pressurized fuel then travels through a drilled circuit in the distributor shaft and is distributed to the appropriate cylinder in the firing order through the hydraulic head of the distributor pump. A metering valve controls the actual fuel quantity pressurized by the plungers. Depending on its position, a helical-shaped groove in the metering valve admits a regulated amount of moderately pressurized fuel into the cavity between the plungers when they are off a cam lobe. Positioning of the metering valve is varied by governor linkage. For 4 or 6-cylinder engines, cam ring distributor shaft guide slot in drive shaft roller support. For 6-cylinder engines, roller delivery plunger chamber. For 4-cylinder engines. Figure 15-25 opposed plunger metering uses plungers arranged opposite one another to meter and pressurize fuel for injection. From metering valve charging port rotor hydraulic head cam. Rotor output port roller plunger pumping chamber outlet port to injector nozzle. Figure 15-26 fuel from the metering valve pushes the pumping plungers apart. The cam ring lobes push plungers together to pressurize fuel, which is distributed by the hydraulic head of the pump. Open metering edge, less fuel, more fuel. The pumping plungers. Electrically avelled sol valve boo. Figure 15%28. This VP44 electronically controlled distributor pump uses the same pumping elements to pressurize fuel for all engine injectors. Opposed plunger metering is also used in electronically controlled pumps. Instead of using a metering valve, an electronically controlled hydraulic flow valve energized by a pump-mounted ECU will open and close the hydraulic valve at a precise time to meter the correct quantity of fuel between the pumping plungers. The Bosch VP-44 pump is a popular example of an electronically controlled opposed plunger metering system. Electronic unit injection. Mechanical and electronically controlled unit injectors are built to create a more compact and serviceable system. A unit injector is a self-contained injection system that encloses a pumping element to pressurize fuel and a nozzle to spray fuel into the cylinder. Unit injectors incorporate pressurization, timing, metering, and atomization functions into a single component or unit, which gives the unit injection fuel system its name. Early mechanical unit injectors, used by two-stroke Detroit diesels, used a compact port helix metering system integrated into each injector. A mechanical governor operated an external control rack. In the 1980s, these injectors were refined and replaced a port helix metering system with an electronically controlled solenoid that operated a hydraulic spill control valve. When the solenoid is energized, fuel is trapped beneath a moving cam-actuated plunger and pressurizes fuel for injection. De-energizing the solenoid ends the injection period. When and for how long an electrical signal energizes a unit injector solenoid can vary how much fuel is metered for injection and enable an electronically variable start and ending of the injection event. A variation of the unit injector is the unit pump. This electronically controlled injection system has a pumping element that operates similarly to a unit injector. The major difference between a unit injector and a unit pump is a line that connects the pumping element and the fuel nozzle located in the cylinder block. Camshaft force 315 low-pressure fuel inlet. Figure 15-29, an electronically controlled unit injector contains a solenoid-operated spill valve and pressurizes fuel using an engine-driven camshaft. Metering and injection timing functions are controlled by energizing or de-energizing the solenoid. Fuel nozzles, electronically controlled unit pumps. Figure 15-30, a low-mounted engine camshaft actuates unit pumps connected to fuel nozzles through injection lines. Pressure time metering systems. Pressure time metering systems were invented and patented by Plessy Cummins, founder of the Cummins Engine Company. Until 2009, the segment-leading ISX engine used lock nut stop nut assembly, coupling plunger retainer, spring injector assembly part number. Figure 15-31, the injector of an earlier pressure time metering system. To meter fuel, a fuel cavity below the plunger is filled by the variable pressure pump. A PT system called the high pressure injection time pressure injection system. In this and earlier systems, metering and injection timing are controlled by varying fuel pressures supplied to a uniquely constructed injector. Inside the injector can fill with fuel. Filling the cavity can take place only when the camshaft operating the injector plunger is on its inner base circle, which is the smallest circle of the injector cam lobe. By varying the low or moderately pressurized supply of fuel to the injector cavity, the amount of fuel metered for injection changes. An element of time is also involved in metering that lends itself to the system's name. As the time that pressurized fuel is available to fill a cavity inside the injectors with fuel varies with engine speed, it can impact the injection quantity. With more or less time available to fill the injector with fuel varies with engine speed, both engine torque and speed are changed. Essentially, PT systems vary fuel pressure according to the time available to inject the correct quantity of fuel to meet constantly changing operator demands for engine power. A variable pressure fuel pump, controlled by a hydraulic governor, changes pump output pressure supplied to all the injectors. Changing pump output pressure controls the amount of fuel supplied to the injectors, which decreases or increases the amount of fuel each injector can deliver. For example, if fuel pressure is increased and Figure 15-32, the variable pressure pump of an earlier mechanical pressure time metering system. Time available for injection is held constant. More fuel is injected into the cylinders by the injectors, because fuel at higher pressure fills the injector cavities faster. Similarly, when the time to supply pressurized fuel to the injectors is decreased, and fuel pressure is held constant, more fuel is supplied and injected, because there is more time between combustion events to fill the injector. Naturally, less fuel is injected when engine speed increases and fuel pressure is held constant. Similarly, less fuel is injected if fuel supply pressure is lowered and engine speed remains constant. Common rail system metering. Common rail fuel injection is the most recent development in high-pressure injection systems, and it is currently used by all new on-road diesel engines. First used in European automotive production in 1997, the features and benefits of common rail fuel systems have made it the injection system of choice for every current production LD, MD, and HD on-highway diesel engine, and for a large portion of Tier 4 non-road engines. Basic common rail injection is simple. Supply fuel at injection pressure to a fuel nozzle that electronically controls the injection event. Although the concept of supplying fuel pressurized at injection pressure to individual injectors is not new, the technology used to switch fuel delivery on and off at pressures now in excess of 42,500 psi while precisely metering the correct quantity of fuel for injection was a breakthrough in manufacturing achievements. The system's metering precision, spray-in pressures, and sophisticated injection event control enable dramatic reductions in pressure control valve rail pressure saucer, high-pressure pump metering unit injectors, communication line sensors, output-input, low-pressure line controller, high-pressure line backflow line, low-pressure pump. Figure 15-33, a gear-driven, engine-mounted, high-pressure pump pressurizes fuel to injection pressure. An electronic control unit energizes and de-energizes the injector solenoids to accurately meter fuel for the injection event. Exhaust emissions and fuel consumption that are accompanied by increased power output and reductions in noise and vibration in engines that use it. Contemporary common rail refers to a classification of several types of high-pressure fuel injection systems, in which pressurization of fuel takes place independently of engine speed. A hollow tube, called a fuel rail, supplies fuel at high pressure to all the injectors. Essentially, all injectors share, or have in common, a fuel rail to supply fuel pressurized to injection pressure. Metering is accomplished by varying the supply of pressurized fuel in the rail to electronically controlled injectors. Because fuel is already pressurized to injection pressure, switching an electrical signal on and off to an injector-mounted solenoid begins and ends the injection event. The quantity of fuel metered is essentially a function of fuel rail pressure and the energization time for the injector signal. Advanced metering functions. LO 15.4 identify and explain the features of advanced metering functions. Metering systems function not only to supply the correct amount of fuel to meet driver or operator demand, but also to control for shot-to-shot variations in injection quantities. This is necessary because the mechanical condition of individual cylinders may result in inconsistent conversion of fuel energy into cylinder pressure. Worn cylinders, misadjusted valves, and variations in cylinder clearance volume are just a few of many potential causes for uneven cylinder power contributions. Another problem is that injectors with the same part numbers may not all deliver exactly the same quantity of fuel for any given identical energization time when they are new, or they may change as they wear and deteriorate. This means there are circumstances when the amount of fuel metered into individual cylinders may need to change or undergo adjustment either from cylinder to cylinder or from one injection cycle to the next to provide a positive benefit to engine operation. The following sections outline more advanced metering system capabilities that help correct for uneven or inconsistent power contributions and address problems associated with abnormal operating conditions. Metering and governor compensation. Before examining more detailed features of metering systems, it is important to understand a governor feature called idle compensation. All diesel engine governors function to maintain a minimum engine speed and limit maximum engine speed by adding or subtracting the quantity of fuel metered into the cylinders. For example, changing engine loads at idle, such as when the air compressor, the power takeoff pump, or the air conditioning compressor engage and disengage, causes the engine idle speed to become unstable unless there is a method to correct load-related speed changes. Built into the operation of the high-pressure injection system is a governor feature called idle compensation. Compensation is observed when a load is added or removed from the engine at idle, and the governor adjusts fueling to maintain a consistent idle speed. Compensation is also seen when one or more cylinders are cut out or disabled during test procedures and the engine maintains a set idle speed. An increase or decrease in engine speed is sensed by the governor, and injection quantities are adjusted up or down accordingly. For example, if fuel delivery to a single cylinder is limited or blocked by a defective injector, or a cylinder has low power contribution because of a mechanical defect, the governor responds to the loss of engine speed and increases fueling to the remaining cylinders to maintain engine speed. The engine's RPM may drop momentarily depending on governor sensitivity, but quickly resumes the set. Technician tip. An engine with a misfire condition is an engine with low or no combustion pressure in one or more cylinders. One of the most common diagnostic techniques used to identify the cause of a rough-running engine is to inspect for misfire conditions by performing a cylinder cutout test, or alternatively a cylinder balance test. A cylinder cutout test is a diagnostic routine many electronic service tools can run, which enables a technician to automatically or manually cut off fueling to a selected cylinder or to pairs of cylinders. A technician must observe whether cutting out a cylinder has any effect on engine operation. When cut out, good cylinders make an engine run rough or rougher. A defective cylinder will not change engine operation. Cylinder balance testing, also called a relative compression test, measures the percentage of power contribution made by each cylinder. It may also graphically display the differences between crankshaft speed acceleration for each cylinder. Cylinder performance test. This test's intended purpose is to help idently weak cylinders instructions select start to modular cylinder contributions, or select back to return to the EDM diagnostics. Less width. This test should only be performed while idling below RPM and with the vehicle out of GE cylinder 1 OK% contribution. VA engine speed 2, OK3, OK 103, average 100%, Stat 4, OK5, OK6, OK0, 2040, 68, 100120140, 01601. 2. Display of a cylinder balancing or contribution test. Averaged together, the cylinders contribute 100%. Weaker cylinders have a lower percentage of contribution. Idle RPM. In fact, as many as 4 or 5 out of 6 cylinders can be disabled during a cylinder cutout test, and the governor will still attempt to maintain a consistent established engine RPM by increasing the amount of fuel metered and delivered to the remaining cylinders. It is important to remember this because a misfiring cylinder in a diesel is not accompanied by reduced engine speed. However, cutting out a cylinder at a speed above idle will reduce engine RPM, which explains why a misfire is generally easier to identify during a cylinder cutout test performed at an engine speed above idle. Cutting out a weak or misfiring cylinder will not lower engine speed, but cutting out a properly functioning cylinder will. Technician tip: operating a misfiring engine under heavy load can potentially cause damage to the engine. If one or more cylinders are not properly contributing to engine power, the governor compensates for a lack of engine speed by increasing fuel delivery to the remaining cylinders. However, as a result, can be localized to the few cylinders that receive a greater quantity of fuel. The excessive thermal loads can cause heat damage to pistons and valves. Metering and idle adaptation. Achieving the smoothest engine idle is a goal of every diesel engine manufacturer, end user, and technician. Variations in the amount of power contributed from cylinders caused by even the slightest changes to fueling results in rough running and uneven engine operation, vibration, and excessive emissions. Uneven power contributions from individual cylinders are caused by a wide variety of factors, including variations to the quantity of fuel injected from cylinder to cylinder and shot to shot within the same cylinder. 1 drop of diesel fuel is approximately 25-28 cubic millimeters. Injection quantity at idle is 210 cubic millimeters. At idle, diesel engines use a fraction of a single droplet of fuel to generate cylinder pressure. Variations in compression and combustion pressures caused by mechanical conditions such as engine wear, valve action, EGR delivery, the condition of piston rings and the cylinder wall, clearance volume, etc. Variation in the manufacturing of injectors, meaning identical injectors can flow slightly different amounts of fuel when energized for the same length of time due to variations in machining tolerance, conductor resistance, and other injector mechanical properties. Deterioration of fuel system components. Even very small changes to the injected quantities of fuel at idle produce rough-running engines and unstable engine speed. Consider that a droplet of fuel has a volume of 25-30 cubic millimeters. A typical idle quantity of injection for most engines is between 3-8 cubic millimeters of fuel. A variation of even 0.5 cubic millimeters corresponds to a 10% variation in delivery quantity and substantial changes in engine operation. In the newest engines, variations to the injection quantities at higher rates of fuel delivery are kept well below plus or minus 0.1 square millimeters. Compare this metering accuracy to the volume of a pinhead, which is close to 1 cubic millimeter. To minimize problems associated with uneven cylinder power contribution, and to ensure that all cylinders have the same consistent combustion pressure, most electronically controlled engines built since the early 2000s use a feature called idle adaptation. Idle adaptation involves making adjustments to injection quantities based on changes to crankshaft speed produced during every power impulse. The crank position sensor can detect slight velocity changes that enable the ECU to subtract or add fuel delivered to each cylinder based on the measured variations in crankshaft acceleration during power events. Data are used by the ECU to calculate and apply a correction factor to the quantity of fuel injected into a cylinder from one combustion cycle to the next. Cylinders with slower acceleration rates may receive additional fuel, while cylinders producing more cylinder pressure than others receive less fuel. Camshaft position sensor, crankshaft position sensor, reluctor wheel. Figure 15-39 in idle adaptation strategy. Consistent cylinder pressure is achieved from signals generated by the cam and crank sensors. Fuel is added or subtracted in each cylinder, depending on how quickly the crankshaft rotates through the combustion and compression events. Cylinder contribution balance codes. If the correction to fuel delivery quantities during idle adaptation becomes excessive, fault codes associated with cylinder contribution and balance are generated. In some engines, an increase or decrease of injection quantities of up to 20% may take place at idle to help balance the contributions made by each cylinder. It is important to remember that contribution-related fault codes are also generated for loss of compression, which can cause uneven cylinder contribution, not just for a loss of cylinder pressure during the power stroke. Cylinder contribution coded when the crankshaft speed changes are outside the expected range, either too fast or too slow. A properly operating cylinder with good compression and combustion quality slows down during the compression stroke, but sharply accelerates crankshaft speed after TDC during power stroke events. For example, if the crankshaft does not decelerate during the compression stroke, there may be a compression leak in the cylinder, or the connecting rod may be bent. Cylinders with bent connecting rods or worn-out rings do not have as much compression pressure to slow the crankshaft as it approaches TDC during the compression stroke. When, how much the crankshaft speed changes are key to differentiating between cylinders with burned valves, bent connecting rods, worn rings, or faulty injectors. Most engines built since 2002 generally have the capability to perform cylinder balance adaptation at idle. Since 2010, faster processor speeds and better engine electronic control units have enabled the adaptive cylinder balancing of cylinder pressures to take place throughout the engine's entire operating range. Technician tip: or idle adaptation values begin to widely diverge. Engine wear or injector deterioration takes place in proportion to the spread between maximum and minimum values. Although no fault codes may be present, it is an important piece of information that technicians can use to make service recommendations about maintenance that may soon be needed. Cylinder and stroke identification. While the crank position sensor detects unbalanced cylinder contributions through inconsistent rates of crankshaft acceleration and deceleration, the cam position sensor is required to identify which cylinder is firing and which stroke each of the cylinders is moving through. In four-stroke cycle engines, the crankshaft rotates twice to fire all engine cylinders and the camshaft once. To differentiate between cylinder 1 and 6, or 2 and 5, or 3 and 4, which are paired cylinders traveling together in a 6-cylinder engine, camshaft position information is required by the ECU. Cylinder firing order is memorized by the ECU, but cylinder stroke and crankshaft position are calculated when data from the crank position sensor are synchronized with the cam sensor. Using a single raised pin on a cam gear, which rotates at 1/2 crankshaft speed, or a missing tooth or a uniquely shaped window in the camshaft reluctor wheel, can typically synchronize the camshaft position to correspond to TDC cylinder 1 exactly at the end of the compression stroke. After the engine has learned the position of cylinder 1, it can count the number of teeth passing by the crankshaft sensor to calculate when and how far the crank has rotated. If the crankshaft sensor reluctor wheel has 60 teeth, the ECU counts waveforms generated by the sensor for 120 teeth to verify that the engine has completed 2 rotations and fired all cylinders. At that point, the camshaft sensor signal and TDC position indicator on the crankshaft may synchronize once more. That is not always necessary, though, because the ECU has memorized the firing order and knows that each cylinder in a 6-cylinder engine will reach TDC position after 120 degrees of crankshaft rotation and 20 teeth pass by the crank sensor to signal TDC for each consecutive cylinder in the standard inline 6-cylinder firing order 53624. To verify that the ECU has received and synchronized both the cam and the crank signals, as displayed on electronic service tools indicating that the sensors have synchronized. This is an important piece of diagnostic information to troubleshoot no-start or hard-starting conditions. A missing cam-crank signal message indicates that one of the sensor signals is missing. After the ECU has synchronized the signals, it can precisely calculate the position of any piston in the engine and the stroke it is on. By measuring the time elapsed between each tooth passing by the crank sensor, velocity changes caused by each compression and power event are measured. Technician tip: failure of either the camshaft or the crankshaft sensor in late-model engines still enables the engine to start and run, because both sensors can provide engine position information. However, the engine may have a longer cranking period if it has a defective camshaft position sensor, because the ECU must guess or attempt to start the engine by using the TDC indicator to alternate the firing order to begin on either cylinder Y or cylinder 6 in a 6-cylinder engine. Some engines even remember the last known good signal from either sensor to reduce cranking time, because an engine may require as many as 3 revolutions before a sync signal between the cam and the crank sensor is established. Gear lash or slack in the timing chain will introduce some error into the ECU's determination of the precise crankshaft position if a crank sensor has failed. Remember, too, that some operating strategies, such as adaptive cylinder balance, depend on precise estimates of crankshaft position, which may not be available if the crankshaft sensor signal is lost, intermittent, or contains errors such as those caused by a defective vibration damper interfering with the generation of correct sensor waveforms. After cranking the engine for some time, if only the camshaft signal is detected and engine position is only approximately identified, the engine may operate roughly or have limited maximum engine RPM. OV52 camshaft. 1 camshaft revolution, SIL 3, SIL 4, 1 crankshaft revolution. The cam and crankshaft revolution. Camshaft sensor signal, crankshaft sensor signal, cylinder balance and emissions. A more critical problem caused by uneven cylinder pressures is not just a rough running condition, but the emissions resulting from uneven or inconsistent combustion pressure. Because formations of various noxious emissions, such as hydrocarbon, oxides of nitrogen, particulate matter, and carbon monoxide, are dependent on cylinder temperature and pressure, as well as on intake charge gas composition. Uneven cylinder pressures can exaggerate emissions-related control strategies. For example, introducing EGR gas into a cylinder with lower than average combustion pressures increases production of HC, CO, and PM emissions. In a cylinder with above average pressure, not enough EGR may be delivered if all cylinders receive the same composition of intake gas. To promote good combustion quality and keep emissions productions low, consistent, and even, cylinder combustion pressures are critical factors to control in today's ultra-low emissions engines. Emissions and adaptive balance. Because of the impact on emissions by inconsistent combustion pressures, almost all engines produced since 2010 can adjust metering to individual cylinders, not only at idle conditions but also throughout the entire engine operating range. Faster ECUs, operating with 32-bit microprocessors, can now provide the processing speed needed to make rapid calculations at high engine RPM. This means cylinder combustion pressures are made to be consistent using adaptive metering strategies all the way to maximum RPM to reduce the production of noxious emissions. Technician tip: consistent combustion pressures from all cylinders are necessary to achieve low engine emissions. If pressure variations exist between cylinders and from shot to shot in the same cylinder, the engine will produce excessive noxious emissions because pressure and temperature conditions change the combustion mechanisms that form NOx, PM, CO, and HC emissions. Because emissions reduction strategies are generally applied the same way to all cylinders, such as the use of the same amount of EGR or injection timing, engines produce significantly different results if cylinder pressures and temperatures are uneven. Even excessive soot in the intake manifold caused by combining oily crankcase vapors and EGR soot can restrict airflow and cause high engine output of NOx. Metering, emissions, and heavy-duty onboard diagnostic monitoring. Fuel pressure, misfiring cylinders, injector energization voltages, cylinder imbalance, timing, injector deterioration, and incorrect calibration codes are just a few of the high-pressure injection system variables monitored by the onboard diagnostic system manager to detect conditions that could potentially cause excessive emissions. Monitoring must also occur during the entire speed and load range of an engine. Failure of any fuel system component can permit emissions to exceed desired levels. Metering and injector calibration codes. During manufacturing, production processes for injector component machining and electrical parts have allowable tolerances. For example, different batches of wiring used to make injector solenoids may have slightly different resistances or microscopic variations in wire thickness. Clearances between machined parts and slight variations in the electrical properties of actuators result in deviations in fuel delivery quantities for any given energization time even, among a set of injectors that are made on the same factory production lines. The result of production tolerances is that no two injectors, whether they have electrical actuators or not, are identical in terms of the quantity of fuel delivered. When injectors are entirely mechanical with no electrical component, they are flow tested on calibration benches, then sorted and grouped together according to similarity of flow rates. Grouped sets of injectors are installed as a set in an engine to minimize the variations in cylinder pressures that could result in rough, uneven engine operation. When injectors have electrical actuators, such as unit type or common rail injectors, the ECU can apply a correction factor to electronically adjust a set of injectors in an engine to have consistent delivery quantities. To develop a correction factor to be applied to an injector's energization time, injectors are flow tested on a fuel comparator bench after production at an OEM facility. During the bench testing, the flow characteristics of each injector are measured. Delivery quantities at different energization times and injection pressures are measured and mapped with extensive detail. With older injectors, only a comparison between the nominal or average fuel delivery of all injectors having a particular part number is made with the actual delivery volume of individual injectors. A calibration number is assigned to the injector based on the differences between its flow rates and an average rate. This calibration number or code generated for each injector is then stamped or etched on the injector. When this code is uploaded to the engine or other fuel system-related ECU, the control unit can apply a correction factor to the actual fuel quantity delivered by the injector into each cylinder. Variations to cylinder pressures are further minimized using this calibration code, which in turn smooths engine operation and reduces exhaust emissions. The appropriate calibration code must be entered into the ECU each time a new injector is installed or an injector is moved to another cylinder. Failure to do so will result in rough engine operation. Actual delivery quantities FFFKNK2 15-47. The calibration code on an injected into the master control module, a proprietary name for the engine control unit on a double D series engine whenever injectors are replaced or relocated to another cylinder. And fault codes associated with cylinder balance and injector calibration. Calibration codes are given different names by manufacturers. Common names for this feature include injection quantity adjustment, ETRIM, adaptation value, or simply older mechanical unit injectors have a batch code assigned to the injector. The best practice for a hydromechanical injection system requires the injector replacement be done in matched sets, with all the injectors replaced with a set having similar flow rates. Technician tip: injection quantity adjustment numbers are assigned to each injector after flow testing during production. Codes are printed on the injector and must be recorded by the technician when an injector is installed. The number code is stored in the ECU using an electronic service tool. Failure to store the correct value for each cylinder can result in rough running conditions, low power, poor fuel economy, and a fault code that illuminates the malfunction indicator lamp. The injector calibration code is also used as a reference point by the ECU to make in-service fueling adaptations that take place when adapting or updating the injector's response to electrical signals to correct for injector wear and deterioration factors. Calibration codes, figure 15-48, are screenshots showing where new calibration codes are entered for replacement injectors. Technician tip: some injectors with calibration codes can only be rebuilt or refurbished by the OEM that produced them. Equipment used to assign calibration codes and benchmark values are proprietary, meaning they are known only to the OEM. Replacement parts, such as nozzles, springs, and other internal parts, change the flow rate and consequently require a new calibration code. Failure to accurately generate and assign a correct calibration code to an injector can, among other problems, cause the emissions to increase beyond legislated standards. Changing an injector calibration code. Whenever an injector is replaced or relocated to another cylinder, its calibration code must be changed. Electronic service tools or service software often contain service menus with shortcuts to make it easy to switch calibration codes between injectors moved to different cylinders. To change an injector calibration code, follow the steps in Skill Drill 15.1. The procedure shown is specific to double D injectors. Follow the manufacturer's instructions for products from other OEMs. Technician tip: just because it is old does not mean an injection system part does not require calibration. Hydromechanical injection pumps are also carefully calibrated to ensure that each cylinder is delivered a precise fuel quantity under different speed and load conditions. Comparator benches are used at manufacturing and service facilities to adjust measured delivery volumes from injection pumps. Such benches, as their name suggests, compare delivery volumes from each line fitting of the pump after a fixed number of strokes or revolutions are made. Adjustments are made to ensure that the delivery quantities match specifications and that vernations between cylinders are corrected. Metering and hunting. Irregular or inconsistent fuel delivery between cylinders or combustion cycles in a cylinder causes the governor to readjust. Skill Drill 15.1, changing an injector calibration code. 1. Place the vehicle's transmission in neutral and apply the parking brakes. 2. Connect Detroit Diesel Diagnostic Link software to the vehicle data link connector and switch on the ignition key. 3. Navigate to retrieve injector calibration. In the menu bar, Entering up the injector calibration window. Remove the valve cover and record all injector calibration codes if this has not already been done. 5. Compare the actual injector calibration codes against the calibration codes in the injector calibration window. If there are any discrepancies between the actual injector calibration code and the codes in the injector calibration window, correct them. If any injectors have been replaced, update the calibration code in the injector calibration window. 7. Enter the engine security password in the DDDL software. 8. Select the transmit function button to upload any calibration code changes to the engine control unit. 9. Run the engine until it reaches operating temperature and confirm that engine operation is smooth. The commanded quantity of fuel metered to correct variations in the engine's speed. A condition called hunting or loping is a rhythmic change in engine RPM at idle speed observed when a sensitive governor attempts to quickly adjust unbalanced cylinder contributions faster than the time it takes for engine speed to change. For example, consider a governor, either electronic or mechanical, that attempts to compensate for changes in engine RPM to maintain idle speed. It responds to a cylinder speeding up the engine by cutting back on fuel delivered to the remaining cylinders. As a result, the engine RPM falls below the set idle RPM. This in turn causes the governor to increase fuel delivery to the cylinders once more, and the cycle of rhythmic speed change repeats itself, with the governor alternately cutting back and increasing fuel delivery without the engine speed stabilizing. The problem is made worse if only one cylinder is receiving more or less fuel, and if the engine has a highly sensitive and responsive governor that quickly attempts to correct engine speed changes caused by the uneven cylinder contributions. Some earlier electronically controlled engines would lose the ability to correctly adapt cylinder contributions at idle when defective injectors or engine faults interfered with the idle adaptation strategy. Injection timing. LO 15.5 identify and explain the principles of injection timing in the high-pressure injection system to promote efficient combustion, clean emissions, and good engine performance. Precisely timed starting points for injection events are critical. Efficiently operating fuel systems must have the capability to change the point during the combustion cycle when fuel injection begins based on a variety of engine operating conditions. The start of injection, also called the beginning of injection, is more commonly referred to as injection timing. Use of either term depends on the manufacturer, but both terms are used in service literature and refer to the same event. SW or buoy is the point in the combustion cycle when fuel enters the combustion chamber. Units for expressing injection timing are in crank angle, degrees relative to TDC at the end of the compression stroke. For example, an SOI of -4 degrees indicates that the injection event begins 4 degrees of crank rotation after TDC, while an SOI of +4 degrees indicates that the injection event begins before TDC. Because there is usually a time delay in the response of an injector nozzle to open to an electrical signal or for a hydraulic pressure wave to be generated by a high-pressure pump, SOI is sometimes more accurately called indicated start of injection. Actual SOI takes place when fuel is observed to begin entering the combustion chamber and follows the indicated SOI. The difference between indicated and actual SOI is called injection lag, a technical term different from ignition lag. This important difference between indicated and actual SOI and the factors that cause injection lag are covered later in this chapter. The end of injection is the point in the combustion cycle when the injection of fuel into the combustion chamber stops. Injected fuel quantity is the amount of fuel delivered to the combustion chamber for each cylinder's power stroke. Injection duration is the time, or length of pulse width, or degrees of crankshaft rotation between SOI and AOI. The injection duration period directly affects the quantity of fuel delivered, which is expressed in units of volume or mass stroke. Variables affecting timing. Injection timing must be changeable in a diesel engine because operating and combustion conditions cause significant variations in the burn rate of fuel and the time available for combustion. For example, as engine speed increases, less time is available to complete injection and combustion events. The duration of those events may not always change with engine speed, but the engine will rotate faster through more degrees of crankshaft rotation. Temperature variables, such as intact air, coolant, and oil temperature, affect not only the duration of combustion events, but also how quickly combustion CA begin. Cold cylinders and air temperatures cause the longest delays to the start of combustion after injection begins because pre-ignition temperatures in the cylinder are low. This means it will require more time for the fuel to absorb enough heat to ignite, resulting in a delay to the start of combustion. how quickly combustion can begin and how long it lasts are also affected by many other factors, such as intake boost pressure, EGR rates, engine load, and speed. As a result, the high-pressure injection system must adapt to these variables by changing SOI and EOI, ignition delay and uncontrolled burn phase. To understand the factors influencing injection timing, first consider that in most engines, peak cylinder pressure during the power stroke ideally occurs at approximately 10 to 15 degrees of crankshaft rotation after TDC. However, there is a delay period between the actual SOI and the ignition of fuel before the piston can be pushed downward in its bore by combustion pressure. After fuel ignites, it is followed by a short uncontrolled combustion period that takes place leading up to the point when peak cylinder pressures occur after TDC, during a controlled burn phase of combustion. Several variables influence how long the ignition delay and uncontrolled burn periods last. Take, for example, the ignition delay period. This is the time period between the actual SOI and its actual point of ignition. The delay or time lag is expressed in degrees of crankshaft rotation. Delay takes place because fuel must be first injected, distributed, atomized, allowed to absorb heat, vaporized, mixed with air in the correct proportions, and allowed to reach ignition temperature before it ignites. These processes take time and are affected by factors such as pre-ignition temperatures in the cylinder, fuel droplet sizing, fuel properties, combustion chamber turbulence, and the quantity of EGR gas in the cylinders. Because the ignition delay period is variable, changes to injection timing should be made to make sure cylinder pressures peak at the optimal crank position just after TDC. Without adjusting the SOI to operating conditions, engine performance, fuel consumption, and emissions are negatively affected. Engine load and injection timing. Engine load is a major factor that affects injection timing. Depending on the load carried by the engine, or the torque it must generate, more or less fuel is injected into the cylinder's combustion chambers. What is critical to understand is how the quantity of fuel delivered into the cylinders affects how long it takes to completely burn. The two most important factors influencing the combustion chamber burn rate are cylinder pressure and temperature. Temperature and pressure affect the speed of any chemical reaction, including combustion. Higher pressure and temperatures tend to speed up reactions because molecules have more energy and are packed closer together. These conditions increase the likelihood of combustion reactions and speed up chain reactions where combustion flames spread to nearby fuel vapors. In the combustion chamber, the addition of fuel causes temperatures and pressures to rise proportionally to the quantity of fuel burned. It is important to understand that adding more fuel to the combustion event means shortening the amount of time it takes to completely burn the fuel. Naturally, the opposite is true. When small amounts of fuel are injected, combustion times are proportionately longer. More fuel is injected under load, and less fuel is injected when light loads or no loads are applied, which means combustion time lengthens and shortens according to engine load. To adjust for the variation in combustion time as engine load changes, the fuel system must have the capability to adapt the SOI based on fuel delivery quantities. When large quantities of fuel are injected, leaving initial SOI timing unchanged, peak cylinder pressures are reached sooner, or even quite a few degrees before TDC. Conversely, under light load operation, when less fuel is injected, fuel burns more slowly. As a result of varying engine loads, the point in the combustion cycle where peak cylinder pressures could occur moves around and would take place outside the optimal crank position unless some correction to the SOI is made. Under heavy engine load, fuel systems should start injecting fuel later than when lightly loaded. To describe fuel injection timing changes or delay in the start of injection, the term retarded timing is used. Retarding injection timing means a later SOI, because it takes less time for large amounts of fuel injected under heavy load to burn and reach peak cylinder pressure. Conversely, injecting smaller quantities of fuel requires an SOI to take place sooner or earlier in the combustion cycle. When fuel is injected sooner, the SOI is referred to as advanced timing. Advancing the SOI is necessary because, under these conditions, light loads. TDC injection 5 degrees before TDC combustion ends 10 degrees after TDC 0.010 1,500 revolutions per minute, full load fastest combustion speed injection. Full load. Injection 10 degrees before TDC combustion ends 10 degrees after TDC before TDC combustion ends 10 degrees after TDC 02C. Injection 15 degrees before TDC. Injection 15 degrees after TDC combustion speed injection 15 degrees before TD1. Requires the addition of more fuel to the cylinders to maintain engine speed. SOI is retarded because combustion time is shorter. Or injecting fuel earlier. Accompanied by small delivery quantities of fuel, fuel takes longer to burn, and more time is needed to reach peak cylinder pressure. Technician tip. High temperature and pressure accelerate the chemical reaction of combustion. Adding more fuel to the combustion chamber increases cylinder temperature and pressure, resulting in shorter combustion time. Under load, higher cylinder pressures and temperatures cause fuel to burn more completely and emit only an observable heat haze, or shimmer, of hot air from the engine exhaust pipe outlet. Observing any smoke from an engine, even without an exhaust after-treatment system, means the engine likely has a defect in the fuel injection system, air induction, or base mechanical systems, engine speed, and injection timing. Another factor that affects injection timing is engine speed. As the engine speeds up, the time required to complete fuel delivery for the injection event and the time required to complete combustion events do not change together. Often, engine speed increases as more fuel is injected, which may take longer for an injection system to deliver larger quantities of fuel. Even if the delivery quantity does not significantly change, it still requires a fixed amount of time to spray all the fuel from the injector tips into the combustion chamber. However, as the engine speed increases and the crankshaft turns through more degrees of rotation per second, combustion and injection events still require a fixed amount of time to be completed and cannot be sped up at the same rate as the change in rotation speed of the crankshaft. Theoretically, at high engine speeds, the fuel system could run out of time to complete the injection event, and there would not be enough time to complete the combustion event either. Leaving the SOI unchanged, as the engine speed increases or decreases, would mean peak cylinder pressure would take place outside the optimal point in the combustion cycle before or after 10 to 15 degrees past TDC. To enable efficient combustion, an injection system must be able to change the SOI in response to changes in engine speed. To understand this, remember that the best engine efficiency is achieved when the peak cylinder pressures are produced 10 to 15 degrees after TDC. If the time required for the combustion process stays the same, taking, for example, 0.003 second, the SOI and combustion speed of fuel should be timed to produce peak cylinder pressures just after TDC. Consider then an engine operating at idle speed, where the combustion event may require 15 degrees of crank rotation to complete. If the engine speed increases, the number of degrees of crank rotation the engine rotates at per second is much greater. The crank turns farther, and the piston moves further up in the cylinder in 1 second at a higher engine speed than at idle. To produce the peak cylinder pressure after TDC in this scenario, the SOI must take place earlier, or injection timing must be advanced. How much earlier the SOI should take place depends on the amount of time it takes for the fuel to burn, and can be determined using the following equation. Degrees of burn time, optimal crank angle, for peak cylinder pressure equal to SOI. General rules for injection timing. The following should be observed with regard to injection timing. When the engine speeds up with no change in load or injection quantity, timing is advanced. Conversely, when the engine speed slows down and load remains the same, timing is retarded. When the engine speed remains the same, but load and injection quantity increases, timing is retarded. Conversely, when engine load is reduced while engine speed remains the same, injection timing is advanced. Table 15:1, Advancing Injection Timing. Technician tip. The terms advancing and retarding injection timing refer to injection taking place earlier or later. But earlier or later relative to what reference point? Usually the reference point is 0 degrees of crankshaft angle, which is the engine position when the piston is at TDC at the end of its compression stroke. An exception to this general rule is when describing the advancing or retarding of SOI relative to another reference point, such as the SOI for a previous injection event. If an engine has an SOI of plus 10 degrees of advance timing, but its SOI changes to plus 6 degrees of advance, it is said to have retarded minus 4 degrees relative to the previous SOI. Injection timing and cold starting. Cold cylinder components and low ambient temperatures create exceptional operating conditions that require adjustments to injection timing. The primary problem of cold cylinder combustion conditions is that they cause a longer ignition delay period. Additionally, cold intake air and cold engine parts that absorb the heat of compression near TDC reduce cylinder compression temperatures. When an engine is cold like this, cylinder pre-ignition temperatures are lower, and fuel requires more time to absorb sufficient heat to vaporize and initiate combustion. The ignition delay caused by these cold conditions results in a louder knocking sound in the engine and affects combustion quality. Inadequate burn time caused by the delay produces excessive black and gray exhaust smoke. To solve the problems caused by cold cylinders and low engine operating temperatures, injection timing is advanced to compensate for a longer ignition delay period. When the engine is running cold, the time lag between the SOI and the actual ignition of fuel can be so long as to cause black smoke. This condition is created because prolonged ignition delay shortens the total time available for combustion before the exhaust valve opens and ends the power stroke. The result of shorter combustion time and lower cylinder pressure is more PM, CO, and HC emissions. Another problem related to cold starting takes place during cranking when igniting fuel becomes more difficult, because insufficient fuel vapor is produced inside cold cylinders due to lower cylinder compression temperatures. Any fuel vapor that is produced tends to quickly condense onto cold cylinder component surfaces. To minimize the effects of cold temperature on fuel vaporization, two separate strategies are often used: retarding the SOI when cranking and advancing the SOI during cold operation just after starting. Retarding injection timing on cold starting. Injection timing is retarded only when cranking, and timing is advanced farther than normal immediately after the engine starts during cold running conditions. The advantage of retarding injection timing during cold cranking is that it allows more time for the piston to rise in the cylinder and generate increased pre-ignition temperatures. When fuel is finally injected, the cylinder is hotter and improved vaporization of fuel occurs. The result is a greater likelihood of fuel ignition taking place and starting the engine. A second benefit is faster cranking speed because there is no combustion pressure that can potentially build up before TDC and resist piston movement if the SOI is retarded. Advancing timing on cold starting. Once the engine starts, cold temperatures and cylinder components delay the start of combustion. This explains why diesel engines that start and run cold have much louder knocking noise, as the ignition delay period is much longer. With less time to vaporize and ignite, raw fuel is also pushed out of misfiring cylinders, creating clouds of white exhaust smoke. If some combustion does take place, the time period from the start of combustion to the moment when the exhaust valve opens is short, resulting in the mixing of soot and vaporized raw fuel to produce gray smoke emissions. To prevent these conditions after the engine starts, it is necessary to advance the SOI to prevent the formation of white, gray, and black smoke generated by vapor from misfiring cylinders and the formation of poorly combusted fuel into black smoke. Advancing the SOI provides a longer time period for more complete combustion of fuel. Built into the fuel timing maps of electronically controlled engines, or the cold start mechanisms of mechanical systems, is a mechanism for advancing the SOI that adjusts injection timing according to ambient air temperature, coolant temperature, and engine speed. Injection timing and emissions. LO 15.6 explain the relationship between noxious emissions and injection timing. To minimize both NOx and particulate production, manufacturers use a strategy of atomizing fuel into smaller, finer droplets that helps shorten the ignition delay period. Smaller, more numerous fuel droplets surrounded by hot air absorb heat and ignite faster. With a shortened ignition delay period, the beginning of injection can take place later to reduce NOx formation. Finer atomization also resists forming particulate, even when timing is retarded, because the smaller fuel droplets ignite and burn faster and more completely. On electronically controlled engines, running SOI in a warmed-up engine is drastically retarded compared with older, mechanically governed engines. Today, injection timing may occur at TDC, a few degrees after TDC or just a few degrees before TDC at idle, compared to the range of 15 to 20 degrees of advanced timing of earlier pre-emission standard engines. The retarded timing produces a gentler rise in cylinder pressure. Table 15:2 Influence of injection timing on combustion events. Relative value optimal timing retarded, advanced start of injection, NOx, HCPM, company figure 15-56 SOI, on older mechanical engines has to be adjusted to within plus or minus 0.5 degree for lowest emissions and to less than 0.1 degree on electronic engines, and lower peak cylinder pressures near TDC, which minimizes NOx formation. On mechanical systems, SOI must be set to within 0.5 degree of the manufacturer's specifications to maintain compliance with emissions certification requirements. Electronic engines have tolerances for variability in injection timing to less than 0.1 degree of crankshaft rotation. Injection timing and onboard diagnostics. Injection timing has always had a significant impact on emissions, which explains why injection timing is a part of the fuel system monitor on world-wide harmonized onboard diagnostic and heavy-duty onboard diagnostic compliant engines. A variety of strategies are used to monitor the precise beginning of injection to ensure that it coincides with expected values. Beginning in 2009, some engines started to use cylinder pressure sensors to measure the rising combustion pressure. Knowing the cylinder pressure for every degree of crank rotation can provide actual SOI feedback to the ECU, enabling it to change indicated SOI and injection rates to minimize emissions and increase engine efficiency. Other engines analyze electrical waveforms from the injector solenoids that are generated by changes to the induction characteristics of solenoid windings when metal control valves near the windings open and close. Most engines, however, use data from the crank position sensor to detect the point when crankshaft acceleration begins due to a combustion event. Crankshaft rotational velocity changes quickly when combustion begins, providing accurate feedback to the ECU about compression, ignition, combustion, and injection events. Fuel injection rate control. LO 15 to 7% identify and explain injection rate control in the high-pressure injection system. In modern fuel injection systems, injection rate is a term used to describe the quantity of fuel injected per degree of crank angle rotation. This term is different from fuel rate, which refers high current connection plug printed circuit board measuring diaphragm, glow plug body sealed glow plug heating rod. Figure 15-50 sensing glow plugs measure combustion pressure for closed-loop feedback to the engine control unit, to the quantity of fuel an engine uses over time, such as the amount of fuel consumed per hour. Injection rate control is the most significant advancement of contemporary injection technology because it influences fuel consumption, exhaust emissions, engine performance, and combustion noise. When an ECU accounts for changes in fuel density due to temperature changes, fuel rate is reported as milligrams per stroke. Injection rate is reported and graphically displayed as the mass or volume of fuel, measured in milliseconds or degrees of crankshaft rotation on one axis of a graph, compared with the delivery volume of the injection event on the other axis. Rate-shaped injection. Injection rate is an important concept for contemporary fuel injection systems because every current injection system incorporates rate-shaping capabilities. By changing the quantity of fuel injected throughout the injection event, the shape of the injection discharge curve is modified, which means an injection system has the capability to shape the injection rate. Rate-shaped injection was first introduced in the mid-1990s, and without it, diesel engine development would have ended due to an inability to meet emissions standards. Rate-shaped injection refers to the shape of the injection discharge curve that is produced by multiple injection events during a single combustion cycle. 602.31.09377537510.74. Unenabled, to the consumption of fuel rate refers to the consumption of fuel rate. Multiplying this quantity times 60% gives fuel mass consumed product. By 60% it gives fuel mass consumed per hour. The newest injection systems can provide several rate discharge profiles by varying injection pressures and the number of injection events. To better understand this, figure 15%-59 illustrates three basic shapes of injection rate that are called lean, clean, and mean. The discharge profiles are named after the characteristic optimized by the injection rate. Each of the three basic rate shapes creates unique properties from combustion pressures. For example, the ramp-shaped clean profile reduces cylinder pressure near TDC to minimize NOx formation. The triangular-shaped lean profile reduces fuel consumption by optimizing cylinder pressure to convert the most power from the least amount of fuel. The rectangular-shaped mean profile creates the greatest amount of cylinder pressure and torque with no intention to reduce emissions or fuel consumption. Injection rate shapes in contemporary engines blend lean, mean, and clean profiles together, depending on engine load and speed. In fact, Most resources and efforts used in calibrating today's diesel engines are spent developing the best combinations of injection rate shape profiles for each engine operating condition, because there is an ideal rate shape for each load and speed condition. For example, to keep fuel consumption and soot emissions low, the injection quantity should be delivered as quickly as possible. This leads to a rapid buildup in cylinder pressure and a longer, harder push on the piston after TDC. Although combustion may be efficient and large quantities of power derived from gas expansion, greater NOx emissions and noise are produced. To achieve lower noise and NOx emissions, it is best to inject fuel slowly at the beginning of the injection event. After each piston travels past TDC and the cylinder volume expands, the injection rate should increase and then abruptly stop. This ramped rate of discharge leads to a relatively slow increase in combustion pressure and lower noise levels. The lower cylinder pressure and temperature produced from this injection rate minimizes NOx formation. If it is not possible to achieve a particular rate, to optimize for clean emissions, low fuel consumption and power, a hybrid shape is used that is created from multiple injections taking place during the combustion period. Alternatively, several of the rate shapes will appear consecutively after one another, with a ratio of clean, lean, and mean rate shapes varying with speed and load. Closed A throttling pintle nozzle B slightly open. Pintle C fully open. Figure 15-60 throttle pintle nozzles shape the rate of injection mechanically through the profile of the needle valve. Manufacturers of common rail systems can currently provide as many as 10 separate injection events from the latest injectors during one combustion cycle. These events can include a post-combustion injection event that is used to dose the diesel particulate filter or lean NOx trap, also called NOx-absorbing catalyst, to regenerate or renew their performance. The low emissions and noise levels demonstrated by the latest engines would not be possible without rate shaping capabilities. Mechanical rate shaping. Before the development of electronic methods to shape injection rate, mechanically governed fuel systems relied on throttle pintle injector nozzles to achieve rate shaping in indirect injection combustion chambers. These nozzles generated a spray pattern that produced a gradually rising rate discharge curve. Such a discharge shape was achieved using a step-type nozzle valve. When the nozzle valve began to lift, a small, narrow, low-volume spray jet was first injected into the combustion chamber. As the needle valve lifted higher with the increasing injection volume, more fuel was discharged from the nozzle because the nozzle valve diameter widened. At this point, the spray pattern changed into a wider, higher-volume cone pattern. Substantial noise reduction was evidenced with the use of these nozzles, along with improved emissions. Later, multi-orifice spray nozzles with a dual-nozzle spring were used in direct injection combustion chambers to mechanically change the injection discharge curve. Similarly, a unique nozzle valve shape is also used in the latest electronically controlled injectors to improve rate shaping. Bosch and its licensees use a double-spring nozzle to control the discharge rate. Each spring is calibrated to lift at a different pressure and volume of fuel. The first spring lifts, sprays fail, drops injection line pressure, and seats again during the initial stage of injection. An internal control piston above the first stage nozzle valve assists this process. As injection pressure from a pump rebuilds, the injection volume increases for the remainder of the injection cycle. Increased fuel volume and pressure supplied to the nozzles is used to lift both springs to supply a larger main injection. This injector operation is illustrated in Chapter 16, Hydraulic Nozzles. Hydraulically actuated, electronically controlled unit injectors built after 96 were one of the first electronically controlled injection systems to use injection rate shaping. Rate shaping was performed mechanically by using a groove machined into the amplifier piston to produce two separate injection events from this electronically controlled injector. Gen 2 Hewis produced 3 injection events using electrical signals applied to 2 solenoids rather than using mechanical control of the injection. This feature is also illustrated in further detail in Chapter 22, Hydraulic Electronic Unit Injector Systems. Pilot injection. Pilot or split-shot injection is a critical injection rate feature and one of the first major types of rate shaping capabilities. As its name suggests, pilot injection operates like a pilot light in a gas appliance or furnace, where a small flame is used to I-valve opens. Ignite a larger supply of fuel when the main gas like a pilot light. Pilot injection refers to a small quantity of fuel sprayed into the combustion chamber 8 to 10 degrees before the main injection. Because the combustion chamber is preheated by the pilot injection and produces an open flame, The larger quantity of fuel injected during the main injection ignites and burns faster with minimal ignition delay. That means fuel can begin to burn almost the instant it enters the combustion chamber. Pilot injection is one of the most effective strategies for minimizing NOx formation and noise emissions while optimizing engine performance. Without having to take into account a long ignition delay period, it is possible to delay the SOI and retard injection timing. And because the ignition delay period is shortened or almost eliminated, there is much less noise produced from an uncontrolled burn period where fuel that is accumulated in the combustion chamber during the delay suddenly ignites and burns at once. This injection rate shaping strategy produces exceptionally quiet engine operation, and the traditional diesel combustion noise clatter is gone. Because fuel is ignited more quickly using pilot injection, more time is available for combustion. The use of multiple pilot injection events allows the use of a retarded SOI to take place even after TDC to help further lower NOx emissions without a penalty to power or fuel economy. Quantity 30 main injection 5. 10 degrees BTDC post-combustion's TDC, TDC degrees of crankshaft rotation. Note the injection quantities and pilot injection event. Crankshaft rotation of 8.4 degrees separates the main and pilot injections main. Combustion injections pilot injections -62. Injection action timing without a penalty to power or fuel economy. Post-combustion injections. Another feature of rate-shaped injection is the use of post-main injection events. Post-main injections are injection events that take place after the main combustion event. By spraying fuel into the cylinder after the main injection event, cylinder temperatures and pressure remain high. Using this injection strategy reduces the production of soot inside the cylinder. The post-main injection event taking place shortly after the main injection adds additional heat and pressure to the power stroke that in turn consumes the carbon that forms soot. A second or later post-main injection event is intended to allow vaporized fuel HCs to exit the cylinder with exhaust gases. This results in much higher exhaust temperatures, which are used to increase the temperatures of exhaust catalysts, allowing them to work more efficiently. Supplemental heating of the exhaust system is needed to regenerate diesel particulate filters. Late post-main injection events provide the HC vapors needed to heat exhaust catalysts and burn away trapped soot. The HC vapors in the exhaust unheat the particulate filter located further downstream. Common Durgo flameless combustion in the diesel oxidation catalyst to rail fuel systems are the only injection system that can supply the additional post-main injection event during the exhaust stroke. 010. Low 15 to 8. Identify and explain the principles of pressurization in the high-pressure injection system. Another important function performed by every high-pressure injection system is the pressurization of fuel. To review, among the most critical reasons for the requirement for high injection are the following. Diesel engines compress dense air mass that requires higher pressure to penetrate fuel. The brief time available for combustion events taking place near TDC requires rapid execution of pre-combustion events such as fuel distribution, where the mixing of fuel and air in the cylinders is achieved through the atomization and vaporization of fuel droplets. Improved atomization requires even higher fuel spray end pressure to reduce noxious emissions and enhance engine performance. Traditional fuel systems have relied on some version of the camshaft and plunger system to pressurize fuel. Although this configuration worked well for decades, it has a number of drawbacks, the most significant of which is that the cam plunger injection pressure is tied to engine speed. This means that at low engine speeds, when camshaft velocity and injection spray in volumes are low, only reduced injection pressure levels are available. If an engine needs to rapidly accelerate, large injection quantities of fuel needing high-pressure injection are not available. This results in poor fuel atomization and distribution, which negatively impacts emissions, performance, and fuel consumption. Under other conditions, high engine speed and low injection quantities distribute fuel too far and fast in the combustion chamber to provide the best pre-combustion conditions. To meet emission standards while optimizing engine performance, injection system pressure for on-highway. Pressurized fuel to injection nozzle pumping plunger camshaft controls 1. Fuel quantity 3. Injection timing when the plunger moves. Figure 15%. Traditional cam and plunger systems control many injection events, controlled with variable injection pressure capabilities. Maximum and minimum injection pressure are reachable independent of engine speed. Pressurization and emissions. Higher injection pressures have the same effect as advanced injection timing because the rise in cylinder pressure is faster when more fuel enters the cylinder per degree of crankshaft rotation. The SOI may remain unchanged, but an EOI that takes place sooner shortens injection duration. This explains why aftermarket performance modifications to common rail injection systems increase injection pressure. Less fuel is burned and more power is produced when injection pressures are higher. Fuel. Atomization low 15-9 identify and explain fuel atomization in the high-pressure injection system. As discussed earlier in the chapter, atomization refers to the breaking up of liquid fuel into smaller, finer liquid droplets. Atomization must take place in order to quickly vaporize fuel, allowing it to rapidly mix with air, absorb heat, and ignite. When liquid fuel leaves the nozzle tip, it breaks up into smaller droplets after encountering friction with air. As an analogy, atomization is like building a fire with either large pieces of logs or kindling. Just as a fire is kindled with small pieces of wood, efficient combustion requires exceedingly fine particles of fuel. Finer atomization means fuel ignites sooner, burns faster, and burns more completely. Breaking the fuel into smaller droplets enhances the fuel's ability to absorb heat, convert to vapor, and mix with air. Fuel droplet size affects combustion qualities, which makes proper atomization a critical injection system function. The ignition delay period is also shortened with improved atomization, leading to lower levels of combustion noise. Better atomization promotes a more complete combustion of fuel, producing lower levels of particulate emissions and improving fuel economy. Finer atomization also means the air-fuel mixture is better able to tolerate the use of recirculated exhaust gas. This is why worn or damaged injector nozzles can result in such poor performance and emissions. However, one difficulty of using finer atomization is that smaller fuel droplets have less mass. This makes it more difficult for these particles to penetrate the combustion chamber air mass compared to heavier fuel droplets. Fuel droplet size and particulate matter emissions. Vapor forms around the fuel droplet as it absorbs heat from the combustion chamber. This means fuel burns from the outside to the inside. Fuel droplet size produces faster conversion of liquid to vapor that in turn results in shorter ignition delay times and longer combustion periods to burn fuel. To achieve the lowest particulate emissions, the finest atomization ensures that each droplet makes adequate contact with air for complete combustion. Fine droplets also allow the use of retarded injection timing for low NOx production. The smallest droplets are produced using smaller and more numerous injector orifices along with high pressurization. Distribution of fuel. Identify and explain the principles of fuel distribution in the high-pressure injection system. Distribution of fuel throughout the combustion chamber is another function of the high-pressure system. The length and angle of the spray holes, as well as the number of nozzle orifices and their diameter and injection pressure, are some of. Figure 15-68 left. Worn nozzle orifices produce large droplets that take longer to burn. Right. Undamaged nozzles result in finer drops that burn efficiently. Figure 15-69 fuel and air are mixed by bowl turbulence to provide low emissions while delivering the best power and fuel economy. The important variables affecting how fuel is distributed in and mixed with turbulent air in the combustion chamber. Larger, heavier droplets penetrate farther and faster because they have more mass, but they do not burn as well as smaller droplets. Modern diesel engines typically have more injector spray holes than older engines. Even the length of a spray hole changes the velocity of fuel leaving the injector tip. Longer holes push fuel at a higher velocity than shorter holes. The angle of the spray holes is also important and must match the shape of the combustion bowl to prevent fuel from simply hitting the piston bowl. In this situation, fuel cannot properly vaporize and does not burn. Figure 15-69. See the symmetrical fuel distribution section of this chapter. Problems with fuel distribution can have a significant impact on combustion quality. For example, in low-emission, high-speed engines, a slow starting or ending of the injection period affects atomization of both the initial and the final portions of the injected fuel. If fuel delivery is not stopped abruptly, the drop of injection pressures at the nozzle tip creates larger diameter spray droplets. The effect is poor atomization and penetration of fuel into the combustion chamber, which causes high emissions and poor combustion quality. Dribbling droplets of fuel at the nozzle tip due to low pressurization also waste fuel. For this reason, the design of any fuel system incorporates features to ensure a sharp ending and beginning of injection that also prevents injection lag. See the injection lag. Figure 15-70 lag is minimized in overhead cam-injected engines. With no push rods to flex, injection takes place quickly after pressurization begins. Section of this chapter, figure 15-70. To properly distribute fuel, spray and pressure at the beginning and ending of injection must be consistent from beginning to end. Symmetrical fuel distribution. Fuel must penetrate the combustion chamber air mass evenly in all directions to mix correctly with air. Without even distribution, proper mixture formation cannot take place, resulting in areas of rich and lean air-fuel ratios and increased emissions. To distribute fuel for optimal mixture preparation, the combustion chamber design and fuel system components must be correctly matched. Nozzle design, nozzle orifice sizing, combustion chamber turbulence, and injection pressure are some of the more significant factors affecting fuel distribution and mixture formation. Nozzles can also wear and be impaired given the hours of operation or distance traveled. Plugged nozzles cause uneven distribution patterns, resulting in performance and emissions problems. Injection lag. LO 15-11 identify and explain the problem of and remedies for injection lag in the high-pressure injection system. Injection lag is not a function of high-pressure injection systems, but a problem encountered while transmitting highly pressurized fuel. The term describes the time delay that occurs between the start of fuel pressurization and the moment when injection actually occurs. In electronic systems, injection lag refers to the delay between the time an injector is energized until the point. Noise. Figure 15%. Vibration isolators clamped to these injection lines are necessary to prevent the lines from cracking. Figure 15%-72 vibration isolator. These common rail fuel lines are necessary to prevent the lines from cracking. Line expansion and contraction is caused by swelling during transmission of fuel in high-pressure injection events. When it begins to spray fuel into the combustion chamber, injection lag influences the accuracy of injection timing controls and the ability of the fuel system to achieve an abrupt beginning and ending of injection. Unfortunately, there is a substantial time lag built into many injection systems. A number of conditions cause lag, and good fuel system design minimizes those factors. For example, while fluids are not considered compressible, time is required to transmit the pressure wave from the pumping element to an injector nozzle. The wave does travel fast, approximately 4,500 feet per second, but it can make slight changes to the SOI at high engine speed operation. A more significant factor causing lag is the swelling of injection lines. In spite of lines having thick steel walls, lines do swell when pressurized fuel travels through them. Enough expansion and contraction of the lines can crack them if they are not properly secured with vibration-absorbing insulators. Fuel volume intended for delivery is lost through swelling line walls. For this reason, high-pressure fuel lines are made not only thick, but also the same length and diameter to minimize variations in fuel delivery quantities and injection timing. Unit injectors, which have no lines between the pressurization stage and the nozzle, have the least amount of lag caused by swelling injection lines because they have no lines. However, if unit injectors are actuated using camshaft-driven pushrods, the flexion of the rods during injection causes lag. Other factors contributing to injection lag include the upward movement of the delivery valve in injection pumps, which causes fuel intended for delivery to the A equal to BC equal to DCD. Figure 15%-73 fuel injection lines must have the same diameter and length to prevent variations in injection quantities and injection timing between each cylinder. Combustion chamber, to be lost through displacement of the delivery valve. The upward movement of the nozzle valve in the injector, which causes the moving nozzle valve to displace some of the fuel intended for injection. Fuel systems incorporate design features to ensure the abrupt beginning and ending of injection. The use of delivery valves in high-pressure lines connecting pumps and nozzles is one example. These valves operate as one-way checks to allow some fuel to remain at a relatively moderate pressure in the fuel injection lines, typically around 800 psi, when the engine is running. The design of the valves ensures that fuel pressure drops far enough below nozzle opening pressure to prevent secondary injections caused by reflecting fuel pulsations in the injector line. These pulses occur when the nozzle valve in the injector closes, suddenly stopping the flow of highly pressurized fuel. The result is a pressure wave that reflects or bounces back and forth inside the injection line from the nozzle to the delivery valve in the injection pump. This effect is similar to the hammering sound heard when shutting off a water faucet in a house. Fuel pressure at the front of the pressure wave can cause the nozzle valve to open, so features need to be built into the system to prevent this from happening. Delivery valves also function to prevent the nozzle from dribbling fuel. Importantly, this effect explains why nozzles are designed to require more injection pressure to lift and open the nozzle valve than to close the valve. Whenever pressure begins to drop in the fuel line, the nozzle valve closes until injection pressure is increased to a much higher level to reopen the valve. WW. A delivery valve minimizes the backflow of fuel into an injection system in order to maintain line pressure between injections. Lag and reactive inductance. Injectors that use magnetic actuators are a major source of injection lag. A phenomenon called reactive inductance or reactive resistance causes a magnetic field to build up relatively slowly in the injector's electrical solenoid. The reactive inductance takes place when an opposing electrical current is induced in any coil of wire, as electrical current flows through it. So, the expansion of the magnetic field, created by the initial inflow of current to the injector, cuts across other conductors in the solenoid's windings and induces current flow in them. The two sources of current initial and induced travel in opposite directions, which produces a high initial resistance in the solenoid. Not only is the magnetic field slow to build up and open the injector's control valve, but also the field takes time to collapse and close the control valve in the injector. An injector's slow response means a large conventional electromagnetic actuator of only one injection event in a combustion cycle. Piezoelectric actuators, which have no magnetic fields, have replaced magnetic actuators in newer high-speed diesels. Fuel System Service General. LO 15-12 outline common inspection and testing procedures for the high-pressure injection system. Fuel system service and system inspection and testing procedures are performed on and off the vehicle using specialized tooling to measure injector flow rates, test actuators, and perform pinpoint tests of electrical connections and circuits, fuel pressure and volume measurement, and software to identify and isolate the cause of OBD fault codes. Common diagnostic tests with OEM or aftermarket scanners and software include performing cylinder cutout tests and balance testing. Other inspection methods involve analyzing visible emissions, often after removing the particulate filters. Troubleshooting misfires. To differentiate between a misfire caused by either a defective injector or damaged or worn cylinder components, the injector in a properly functioning cylinder can be swapped with the injector in the suspect cylinder. Movement of the misfire code to another cylinder that comes after the suspect injector is moved indicates a defective injector and not a problem with cylinder components. To identify a misfiring cylinder that causes engine noise and vibration, a cylinder cutout or balance test is useful. On hydromechanical engines using pump line nozzle fuel systems, an injector line can be loosened, which prevents injection of fuel to that cylinder. Scan tools or computers running software capable of bidirectional communication can also electronically cut out fuel delivery to individual cylinders. A measurement can then be made of the extent to which more or less fuel is injected by other cylinders to compensate for the lost contribution from a particular cylinder. The acceleration and deceleration speeds of the crankshaft are also monitored to identify cylinders with low combustion pressure. A cylinder cutout test detects misfiring or a cylinder with a low power contribution. In the cylinder cutout, Figure 15/77 displaying cylinder cutout testing with after multiple cylinders cut out for testing. Test. The contribution may not be present. A technician must observe how the engine runs with a particular cylinder cut out or de-energized. A properly contributing cylinder causes the engine to stumble and vibrate after it is cut out, and performance improves when it is reactivated. Unusual noises that disappear when the cylinder is cut out pinpoints mechanical conditions to a particular cylinder, performing a cylinder balance test to identify weak cylinders that are contributing to low power complaints and causing rough running conditions. The software diagnostic routines of all late-model diesel engines include some variation of a cylinder balance test. A cylinder balance test, the crankshaft velocity changes for each cylinder compression and power stroke to identify cylinder misfiring, unbalanced power contributions, and mechanical problems with an engine, such as a bent connecting rod or burned valve. Many fault conditions produce unique patterns of velocity changes in the crankshaft. For example, low compression due to a mechanical fault will fail to slow the crankshaft down on the compression stroke in comparison to a good cylinder. The crank position when deceleration occurs will also be delayed. Weak injectors can be identified by measuring how much correction the ECU needs to make to injector pulse width, by measuring the quantity of fuel delivered by other injectors to compensate for a weak cylinder. Crankshaft acceleration data during the power stroke is used to calculate the correction factor. On a double D series engine, the idle speed compensation number derived during a cylinder balance diagnostic routine indicates how much correction to the injector pulse width signal is required to produce the same crankshaft acceleration from each cylinder. For the cylinder balance test, follow the steps in Skill Drill 15.2. Skill Drill 15.2 performing a cylinder balance test. 1. Start and run the engine until it reaches operating temperature. Place the transmission in neutral and apply the parking brakes. 2. Connect Detroit Diesel Diagnostic Link software to the Vehicle Data Link connector. 3. Navigate to the Instrumentation menu and then to the Fuel System tab. 4. Observe and record the idle speed balance values for each cylinder while the engine is at idle. 5. Analyze the results. The Master Control module will apply a positive or negative correction factor to the length of the injector pulse width. A positive value means more fuel is injected to compensate for low cylinder pressure. A negative value indicates that a shortened pulse width signal is used to remove some fuel from the cylinder. A 100% change means the MCM cannot add or remove any fuel, and the cylinder contribution will not be the same as other cylinders. Generally, any value less than 70% indicates a problem with the cylinder. These problems range from the need for a valve adjustment to defects in the injector, the high-pressure fuel system, or a base engine mechanical condition. Analyzing particulate matter formation. Ideally, only a heat wave should be observed from the exhaust pipe of a diesel engine when under load. When black or grey exhaust smoke is present, it is because of excessive particulate emissions, although they are the most common emissions-related problem associated with diesel engines, and for that reason visible during on-highway operation. They also indicate a problem with engine operation. Excessive particulate emissions are produced typically under the following conditions with their respective causes. 1. Large fuel droplet size. Worn nozzles and spray holes. Low injection pressures, nozzle dribble. 2. Poor mixing of air and fuel. Inadequate combustion turbulences, restricted airflow. Excessive fueling of combustion chamber. Incorrect valve timing or adjustment. Poor distribution of fuel in chamber. 3. Inadequate pre-ignition temperatures, low compression pressures, low intake temperatures, excessive ignition delay. 4. Inadequate combustion time, incorrect injection timing, excessive engine speed, incorrect valve timing or injection timing, excessive ignition delay time, cold ambient temperatures. Technician tip: not all diesel smoke means engine trouble. Some older engines lack exhaust after treatment devices. During acceleration or when shifting gears, these engines momentarily produce a puff of smoke and within a few seconds produce clear exhaust. Anything more than this indicates some engine fault. Law enforcement agencies often use standards of no more than 15 seconds of visible emissions during 1 minute of operation to assess emissions-related penalties. Wrap up. Ready for review. Diesel engine fuel systems have two main divisions: the low-pressure transfer system, which stores and supplies fuel for the injection system, and the high-pressure injection system, which delivers fuel to the combustion chambers. Efficient diesel engine operation relies on the injection of a precise quantity of fuel, injected at high pressure at the correct time into the combustion chamber. High-pressure injection system operation is better understood by examining functions common to all injection systems. High pressurization of fuel is necessary for several reasons. Fuel must have sufficient pressure to penetrate the dense combustion chamber air mass at high rotational speeds. Only a short amount of time is available for the injection of fuel, and high pressure is necessary to break up the liquid fuel into a fine mist. All high-pressure injection systems perform the following tasks: meter the correct quantity of fuel for injection, time the injection of fuel, control the rate of fuel delivery, atomize fuel, and distribute fuel throughout the combustion chamber. Diesel engines meter only fuel to control engine speed and torque. Metering is the process of measuring and delivering the correct quantity of fuel required for each cylinder for the various speed and load conditions of the engine. To vary vehicle speed and power output, pressure in the cylinders must increase or decrease by changing the amount of fuel injected and burned. Increasing combustion pressure inside the cylinders increases engine torque output. All diesel engines use governors to regulate the quantity of fuel injected into the cylinders. A diesel governor equivalent in a gasoline or Otto cycle engine is the throttle plate, which is controlled by a driver. Even very small changes to the quantities of fuel injected at idle produce rough-running engines and unstable engine speed. To minimize problems associated with uneven cylinder power contribution, most new electronically controlled engines use idle adaptation to make cylinder pressures consistent. Consistent combustion pressures from all cylinders are necessary to achieve low engine emissions. Emissions reduction strategies achieve consistent results when they are applied the same way to all cylinders operating with identical pressure. A. To correct individual variations in flow rates. Many newer injectors are assigned calibration codes to compensate for manufacturing tolerances to injector flow rates. A. For efficient combustion, clean emissions and good engine performance, precisely timed injection events are critical. Efficient fuel systems must have the capability to change the point when fuel is injected based on a variety of engine operating conditions and control algorithms.